So hopefully you're seeing my movie recording. No quiz before break, pretty please. Would you rather have the quiz the Tuesday after break? Probably not. We'll have a quiz before break. It'll be easy. Maybe one of the questions will be, are you on break yet? And the answer should be no. Anyway, so what I wanted to talk about is the dissolving metal reduction, which you've seen before. And the dissolving metal reduction is just a solution of an alkali metal. Just take the metal in its zero oxidation state in liquid ammonia. And often these reactions are done at minus 33 degrees C because that's the boiling point of ammonia. So there'll be like a dry ice condenser on top to keep it going there. And when you stick lithium in liquid ammonia, it donates its electron to ammonia. It's called the solvated electron. And it's actually pretty cool. You've got a lithium cation, and that's surrounded by the nitrogen lone pairs. Right, so that's heavily solvated. And since it's a pretty small ion, that's a relatively strong solvation force. But then you've just got an electron by itself floating around in solution, surrounded by the partially positive hydrogens from the liquid ammonia. So it's kind of weird. I mean, normally you don't think of electrons being able to just float around in solution like that. And it's cool because it's a very dark blue solution. So it's colorless liquid ammonia, and then you put your lithium in there, and it immediately turns this deep dark blue. So it kind of tells you when the reaction is done too, because the blue color will fade once the electrons are used up. So this solvated electron is a very strong reducing agent, right? Remember the definition of reduction? What's the definition of reduction?
Adding hydrogens or removing oxygens.
Okay, that's the OChem definition of reduction. What's the definition of reduction back from Gen Chem?
Loss of electrons.
Loss of electrons is oxidation. Leo the lion goes grr.
Okay, well the other one.
Or oil rig. So gaining electrons, right? So a strong reducing agent is going to be oxidized, is going to give up electrons. It doesn't get much stronger of a reducing agent than an electron by itself floating around, right? So it will reduce lots of things that are not ordinarily reduced. So what have we seen it so far reduce? Is one from chapter 9. Right? There was a reduction where you can take a disulfide and reduce that sulfur-sulfur bond by treating it with lithium and liquid ammonia. I'm using lithium, but it doesn't really matter. You can use any alkali metal. Could be sodium solid or potassium solid as well. So any of those will donate their electron to ammonia. And what you'll get out is, in this particular case, the lithium salt and two equivalents of that. And I don't think I talked about the mechanism of how this reaction goes, but basically what you're looking at is you're looking at donating an electron into the sulfur-sulfur bond. The lowest unoccupied molecular orbital for this disulfide is actually a sigma star orbital that looks like this and has a node down the center between the sulfur atoms. So if I donate an electron into that, right, that electron will go into that orbital. What I end up with is weakening that bond and creating what we call a radical anion. So now there's an extra electron on that sulfur. You can see that the orbital is symmetrically distributed about the two sulfurs, which means so is the electron. I've drawn this Lewis structure with it on that sulfur, but that electron is evenly distributed over the two sulfurs. And because we're donating an electron into an anti-bonding orbital, we've now reduced the bond order to 0.5, right? Because there's now one electron in the anti-bonding orbital to go along with the two electrons in the bonding orbital. And that weakens that bond. And if you donate a second electron in, right, onto the other sulfur, then you'll turn that bond order into 0, and you'll actually split that bond, right? So the second electron causes the bond to break. Because the pKa of the thiol is 12, we don't actually protonate that to create the thiol until we do an aqueous acid workup. So we got aqueous acid, right, and that will generate the thiol. So the net reaction is the reduction of the disulfide to the thiol, and we get two equivalents of the thiol, but the product of the dissolving metal part is just the salt. So that's one reaction that you've seen before for dissolving metal reduction. I think it was actually even on the exam. The reaction that we're working with now is similar, right? Except now we're working with a carbon-carbon triple bond, and the lowest unoccupied molecular orbital is pi star. So the electron is going to donate into that pi star orbital, right? And that's got nodes both on the plane and perpendicular. So that's going to weaken the pi bond. It's going to turn the pi bond, right? Instead of having a bond order of 3, you're going to have a bond order of 2.5, basically 1.5 pi bonds. It's going to create a radical anion again, just like we created a radical anion on the disulfide. But now you can't actually draw a Lewis structure, right, that has an extra electron on carbon, because carbon can't expand the octet the way the sulfur does. So we have to change this to a carbon-carbon double bond, and we've got a radical on one side and an anion on the other. The second electron then donates to fill that orbital, and you generate a dianion. And these negative charges want to get as far apart as possible, and these sterically bulky methyl groups also want to get as far apart as possible. So we have both an electronic reason and a steric reason why the product should end up being specifically the E, or the trans-alkene. Okay. But now, because the pKa of the vinyl group, right, the sp2 carbon-hydrogen bond has a pKa of about 44, and ammonia has a pKa of around 35. Now ammonia is a good enough acid to donate that hydrogen. And so the product will actually be the alkene. We've still got a lithium salt here, right? These are, I haven't been putting the lithium in there, but these are the lithium salts. And the other product will be the lithium amide, LiNH2-. And then this one can do it again. The pKa of this hydrogen is actually going to be higher than 44 because it's a monoanion already, and you don't really want to create a dianion. So we don't know, I don't know what this pKa is, but I know that this dianion is a stronger base than this monoanion, and the monoanion is already a strong enough base to deprotonate ammonia. So you don't need an acid workup, except, of course, to get rid of that. So there is an acid workup step, but it's not necessary to generate the product, which after the second proton transfer will have generated a second equivalent of lithium amide and the trans-alkene. So this you saw in the video, right? I hope. And we know that this reaction gives E-alkenes exclusively, which is in contrast to the reaction with catalytic reduction, where you're working at a metal surface, and since the metal surface delivers the two hydrogens from the same side, then you've got a cis-alkene, right? So we know that we can generate the cis-alkene by catalytic hydrogenation. So there are other reactions that the dissolving metal reduction will carry out. And one of the things it will do is it will actually reduce the benzene ring. The benzene ring is pretty inert. It's stabilized by an aromatic stabilization energy, which is actually about 30 kilocalories per mole. But the dissolving metal reduction will actually reduce that and give you a diene, and this is called the Birch reduction. And I'm not sure that the Birch reduction is something that I covered in the videos for this chapter. So the question I'm going to ask you is, can you imagine how this dissolving metal reduction might accomplish the transformation I just showed, where we have two hydrogens? We basically added hydrogen in a 1,4 sense across the double bond. And it actually gives this product in particular. It depends, the product that it gives depends on what's actually attached. So if instead of having this group with lone pairs, which is electron donating, I've got this carboxylic acid, which is electron withdrawing, the double bonds actually go into a different place. So we've still added hydrogen across the double bond, but in this case we've added it to position 1 and position 4, whereas here we add it to position 2 and position 5. So who would like to propose what's probably going to happen when we take the benzene ring and we confront it with the dissolving metal, which is basically an electron floating around in solution? So I'm just going to write it as E-, but you know that that's solvated, surrounded by the ammonia. If I were to ask you to propose a mechanism for this, knowing only what we just looked at, which is that it gives a product that has hydrogen added to these two sides. So I'm going to draw the hydrogens in there. What would you do? Panic is an option, but not a productive one.
I would do the same, like a similar process to the one we did that gives the E-alkene.
Right, so we donate it into the LUMO, whatever the lowest unoccupied orbital looks like for the benzene, which you don't actually know. But what you do know is that right now all of these carbons have 4 bonds, which means that you're not going to be able to just add it to a carbon without expanding the octet, which isn't allowed. So if we add this electron to this pi bond, for example, right, to this end of the pi bond, we're going to have to break that pi bond. And if I break that so that one electron goes in each direction, what I'm going to end up with is a radical anion, right? So I'll end up with a radical on this carbon, and over here I've just paired it up, so I'd end up with a radical anion that looks like that. And that's very similar to what we just did with the alkene, right? We ended up with a negative charge on one end and a radical on the other end to make the radical anion. and then we added a second electron to generate a dianion. So you might imagine that we're going to do the same thing. We're going to add a second electron here, and then we would end up with a dianion. Oops, that bond's gone. But this is probably not the best resonance structure of that dianion, right? Because those two negative charges are now right on top of each other. What can I do to generate a more stable resonance structure?
You can make it the 2,5 instead of right next to each other.
So I'm basically going to push this pair of electrons in and make a double bond here, and push the other pair of electrons out to generate a resonance structure that, just like the alkyne case, puts those negative charges as far apart as possible. So it's the same principle. It's kind of nice when the same principle allows you to explain multiple reactions. So we maximize the separation of the negative charges. There's no steric factor to contribute here like there is with the alkyne. It's all electronic. But you'll notice that this intermediate is more stable than the other possible intermediate. The other possible intermediate that could have resulted if I'd added the electron to the other end of the double bond in the first step, the other possible intermediate that I could have come up with is this one. And that's less stable. Why is this less stable than that one? Any ideas?
I think the top one, it's tertiary, and I think the tertiary one accommodates positive charge better.
That's true. Accommodates positive charge better, but this is negative charge we're trying to accommodate.
Right, but so that's why I'm saying it's wrong.
But it does make sense that if something accommodates a positive charge, like the positive charge would be stable here because of the electrons donating in from this lone pair. If positive charge is stabilized, then negative charge is probably destabilized. So the lone pair is electron donating to the ring. So you want to take the negative charge and keep it away from the position adjacent to the lone pair. And that's the opposite to what you would want if you had the carboxylic acid present there. Because imagine if I had the carboxylic acid here and I had the negative charge on that adjacent position, so I'd made this intermediate. In this case, I can actually stabilize that negative charge by pushing it out onto the carboxylate. So there's a resonance structure that gets that negative charge out onto the oxygen, and that's going to be the most stable possible resonance structure. So the COOH group is electron withdrawing, and this will become relevant next semester, but the OCH3 group is electron donating. And that's why we see the opposite regiochemistry in the Birch reduction of the aromatic ring. So going back to the intermediate with the methoxy group on there, that's the most stable resonance form. What happens next, do you think? All right, we've generated the dianion as the lithium salt. should ammonia be a good enough acid to protonate that benzene ring? What's the pKa of a benzene hydrogen? So the answer is yes. Screensaver tried to turn on. Are we back? So the answer is yes, it is a good enough acid, right? Because the pKa of ammonia is still 35, and the pKa of an sp3CH bond, which is what we're going to be looking at, is higher than that. The pKa of this hydrogen, because it's adjacent to a double bond like that, is actually closer to 40 than it is to 50. But it's still higher than, right, it's still a weaker acid than ammonia, which means that we can generate the lithium amide just like we did before. Right. So you don't need an acid workup here except to get rid of the lithium amide. You can deprotonate ammonia twice with these lone pairs to generate the actual product. Which is the cyclohexadienes. This is a 1,4-cyclohexadiene. If we number it like this, the double bonds start at carbon 1 and carbon 4. So that's the Birch reduction. And there's another reaction that the dissolving metal reduction will do, which is it will take a carbonyl group that has an adjacent pi bond and reduce the pi bond. So lithium in the zero oxidation state, just the metal solid, and ammonia liquid. And follow that up with an aqueous acid workup. That will generate the plain old ketone. So it reduces what we call an alpha beta unsaturated carbonyl compound. To give just reduction only of the carbon-carbon pi bond, but not the carbon-oxygen pi bond. So that's a useful selective reduction. Whereas lithium aluminum hydride would reduce the carbon-oxygen double bond and not touch the carbon-carbon. So if we use the standard lithium aluminum hydride in ether, followed by aqueous acid workup, we get the opposite result, where we reduce this to an alcohol and the carbon-carbon pi bond stays put. So hydride reducing agent has the opposite effect. So those are 4 different reactions, 2 of which are more relevant to the second semester than they are to the first semester, but very similar